All right, let's get started. So today we want to talk about stack and queue. But first we got to clean up a topic that we didn't get to last time, deleting a node from a linked list. I had these two slides at the end of lecture. I couldn't get them in last lecture. I didn't think I would be able to, but it's fine. We can just do them right now. So deleting a node from a linked list. How do we do that? And this is the kind of capstone of task 3, programming task 3, is deleting a node from a linked list. So it's something I definitely at least want to get out there. I would say this is the bulk of the difficulty of task 3 is deleting a node. When you have to delete a node from a reviewer ID, we have a reviewer that may or may not have reviewed a song, but for whatever reason, they either want to withdraw their rating or maybe they got banned or something. We're going through and removing their ratings. But you have to remove their rating from a song. So to delete a node, let's say we want to delete this node with the value 2. What we're going to need is a reference to the previous node in the list to be able to do this. So to delete this node, we need a reference to the node that comes before it. And then we're going to update next to the node that we're going to delete next. So to delete a node, conceptually, it's not, there's not much going on. We just update a next reference. This is the beauty of linked lists. We have all these nodes all over in memory, and we link them together with these references. So if we want to make a change to the list, we just update one of the next references. So by doing this, we take the node that comes before the node we're going to delete and update its next to be the next node in the linked list. We just change that to effectively bypass this node that we're deleting. So we don't actually delete that node at all. We just update the references, update a next reference to bypass that node. It's effectively cut out of the list. It effectively is no longer part of a list. It's technically still a list of size 2 with the values 2 and 1, but it's cut out of this list that we care about, that we have a reference to. We'll have a reference to this head of the list of 4. And since we can no longer access that node, we can't access that object, it's going to be garbage collected. Java is going to, at its leisure, clean that up, delete that from memory, because we no longer have a way to access it. So conceptually, just update a next, and that gets rid of that node completely. In practice, that's a bit trickier. So for your task 3, there are a few methods that you write that I think are kind of just warming you up to this one. Adding a rating, which is just append, which you already have the code for. Finding whether or not a certain reviewer has rated the song. Navigating through the list and finding a value. We've done find. You have to modify it a little bit. You have to do a little bit different to make sure you're not just taking that code, I guess. But find if the reviewer has reviewed the song. Those are really warming you up to the idea of a linked list. You finally have your hands on a linked list. We've been talking about it in lecture all week. But that's where you finally get your hands on one in the code and see how to actually work with these things. And then adding ratings, but not letting a reviewer rate a song more than once. That's just, I've said it already, but that's getting you practice with a linked list. Once you get to the last one, I would say, in my opinion at least, this is the bulk of the difficulty. When you have to remove a node by reviewer ID, there's, I'd say, 3 things that you really have to be aware of that make this a bit trickier. One, you need a reference to the node before the node that you're going to erase. So once you find a node with the right reviewer ID, you need a reference to the node before it so you can update its next to cut that review out of the list. So you're navigating over 2 nodes simultaneously. So figuring out how to do that, especially how to do that without getting any null pointer exceptions, is a little bit of a challenge. It's not overwhelmingly so. I think it's fair. I think it's a fair question. But it is difficult. It is a step up in difficulty from task 1. And so that's the first one. You got to navigate through, look at 2 nodes at the same time. And then the other 2, what if the that the rating that you're removing is the head of the list? And what if the review you're removing is the last element in the list? So kind of two edge cases that immediately jump out at us that need to be addressed. What happens when the node you're removing is either the front or end of the list? So we got to think about those two when we're deleting. And all those are special cases. You got to have extra code to handle all those cases. So if you're getting through those first three parts of task 3 and you're cruising along and you're feeling good about everything and you're like, I only got delete left, this will be easy, just allocate your time accordingly and expect the deleting a node to take you, I would guess, at least half of the time on the homework is going to be just coding up delete. So just be aware of that. I just want to make sure that you can all plan ahead, plan accordingly, allocate your time however you need to. So that's deleting a node. And we don't have any code for that. It's up to you to code delete. We really help you out with the first one, adding. We give you the code. We kind of help you out with the second one. It's a find. We gave you code for find, but you have to modify it. For the third one, delete. By that time, you got to know how a linked list works and be able to implement this. And it is, there was some chat in Piazza too, and I'm sure everywhere. But task 3 is a jump up in difficulty from task 1 and 2. Tasks 1 and 2 are pretty much easing you into the course, easing you into Java, getting used to this new language, the new syntax, setting up IntelliJ. There's a lot of extra things involved with those first two tasks that aren't really related to programming. At task 3, that's the first one where Paul and I designing the course and everything. Task 3 is the one where it's like, okay, they're settled in, they're taking the course now, they got IntelliJ set up, we don't have any silly issues like that. Like, they're ready to sit down and start coding some stuff. So we are expecting it to be able to write more complicated code from task 3 forward. So I would say tasks 1 and 2 were the easy ones, where we're just easing you into things. Task 3 is it's where things start. It's where I don't have a PG way of saying it, but it's where things start. So any questions on that before we get into stack and queue or on anything else? And again, it's not overly hard. I don't want to scare you or anything, but it's just plan more time for task 3 than tasks 1 and 2. Any questions before we get into stack and queue? When I don't give warnings like that, the whole class is mad. Like, what the hell? I thought this was going to be just like task 1 and 2. So I just want to be upfront about things. Okay. Stack and queue. So we're going to talk about stacks and queues. These are, we're going to build a stack and a queue. We're going to see the code for both of these types, both of these classes. And we're going to see that both of these, we're going to build them both on linked lists. These are very efficient to build with linked lists. And they're going to effectively just be the linked list, except we're going to restrict their functionality, which in my, I think it's a little controversial. I don't really like stack and queue data structures, to be upfront about that too. The data structures are, full data structures, a full linked list, but we're going to artificially remove a lot of the functionality in the name of efficiency, in the sense that we're only going to expose efficient methods that you can use. My pushback on that is, why not just use a linked list and be careful about what you're doing and just use it efficiently, because you might want those extra features that are restricted from a stack and a queue. You might actually want those features someday, and if you're using an actual stack or queue class, you don't have that option. That said, the concept of stack and queue are critically important. You have to understand how stacks and queues work if you're going to do anything in computer science or software engineering. These are just fundamental data structures that you have to know how they work conceptually. But in your code, understand the concept, and then if you use some other data structure, like just a raw linked list, and then use it as a stack or a queue, it's usually the better option, in my opinion. So let's get into these things. Stack. You know what a stack is? I always think of a stack of papers or a stack of folders in this case. When you stack when you stack up values, you can only access the top of the stack. Whatever the top element is, that's the only one we can access. So we have this stack of folders. We can only access this top element, this top folder, and we can only add folders to the stack or remove the top folder from the stack. Now, technically, if we're really careful, we could get one of these in the middle. But conceptually, the computer science concept of a stack, we're not going to allow that. You can't access a value in the middle of the list. You can't even access the second folder in this list without removing the top one first. And we've seen stack. We're familiar with stack as a data structure so far because we've been using stack memory all semester. So stack memory is a stack of stack frames. So when you have a stack of stack frames, and we show this visually kind of backwards. We have our stack upside down. In our memory diagram, the stack goes down. But conceptually, it's the top of the stack. Whatever stack frame is on top of the stack, that's the only active stack frame. We can only access the top value of a stack. So the top stack frame, whatever variables are in that stack frame, those are the only ones we have access to as our program is running. We can't go down the stack to a different stack frame and see what those variables are. We just can't do it. The only thing we can do is add new stack frames to the top of the stack when we call methods and remove stack frames from the top of the stack when the stack frame at the top returns, when that method call returns. And when a stack is removed from the top of the stack, when a frame is removed from the top of the stack, which happens when a method returns and we cross it off, control goes back to the next stack frame on the stack. So we remove the top stack frame, whatever's underneath it, that one is now the active stack frame again. So it's a stack of stack frames, very literally a stack. The conceptual stack that we're talking about here. So if you're ever in the middle of a memory diagram, maybe you have to go do something, you get distracted or something, you come back to your memory diagram and you're like, what's the active stack frame? You look at the bottom of your diagram and you go up until you see a stack frame that's not crossed out. That's the one that's running 100% of the time. I mean, as long as your diagram's doing what it's supposed to do. That's the active stack frame. Whatever one's visually on the bottom, that's the top of the stack. That's the active stack frame. Stacks have two methods, and two methods only. Push and pop. Push an element to the top of the stack, pop that element off of the stack. Some implementations you see will have a third method. Sometimes it'll be top or peek, something that lets you look at the top element of the stack without removing it. Our implementation is going to be just the bare bones two methods that are required. Push to the top, and then pop. If you want to look at what the top element is, you do have to remove it, and it gets returned. So we're going to see the code for this, but let's see how it's used first. We're going to create our new stack. We're going to push 1, 2, 3 on the stack. So we push 1 to an empty stack. That gets on the bottom. Push 2, push 3, and we have our stack, 1, 2, 3. And if we pop from this stack, we're going to get the top element popped off, and then X is going to be storing the value 3. That's what was popped off of the top of the stack. And here's how we do that. In toString, I wish I should have removed toString from the slides. We have toString in the repo, just so when you're running the example code, you can see what's in the stack. But toString wouldn't actually be there. It's not either push or pop. Therefore, not allowed. It's not part of a stack. So to build our stack, we're going to build it using a linked list. We're going to store a reference to the head of the linked list, which is going to be the top of the stack. And when we push, we're going to prepend to that list. We have an extra... Oh, no, we don't. So we're going to prepend to the list. So we're going to start top off as being null. And then whenever we push, we're going to append this .top is going to equal a new node with the value we're pushing and a reference to the old top. We've effectively prepended to this list. When we pop, we have a little more work to do, but not too much. When we pop, we want to first check if the list is null. If top is null, the list is empty, and we're trying to pop from an empty stack. A lot of implementations are going to give you an error when you do this. Your program crashes. If you use Java's built-in stack and you try to pop from an empty stack, just create new stack, stack.pop. Program crashes, throws an error, and nothing works. We're going to be a little more fault tolerant here. We're just going to return null. You shouldn't be popping off an empty stack regardless, but we're going to return null if we pop off an empty stack, just the way that we're going to build it. If the stack is not empty, we're going to grab the value at the top node. That's going to be the value that we're going to return to the user. We're going to return that value to the user. And before we return, we're going to update top to be a reference to the second element in the list. So we're going to update top's next to be a reference to this.top.getNext, the next element, the second element. Which means we've effectively cut the first element out of this list, and it doesn't exist anymore. It's going to get garbage collected. Any questions on how a stack works? Let's see, in one of these abbreviated memory diagrams, so we're going to create a new stack. Top will be null. We're going to push 3, push 7, push 2. Each time we push, we're prepending and updating top to be a reference to the node that we prepended. And these would be 3 objects. If we were doing the full memory diagram, these would be 3 objects in the heap, all with their own reference numbers. And then top would store a reference to this node. Then each next is a reference to the next node until the last one. Next is null. When we push a 4th element in this example, we're going to do the same thing. We're going to prepend a new node with the value -5, and next referring to the old head of the linked list. And then update top to be a reference to that. When we prepend, this is a nice feature of prepend in a linked list. Notice that everything in the red box, our old list of size 3, is completely unchanged. When we prepend an element to a linked list, we create a new node with the value we're prepending and update next to refer to the old head of the list, meaning all the changes occurred right here. We updated the value of top, we created a new node that references the old list. The old list is completely unchanged. So this really says a lot about the versatility of a linked list. We have all these nodes throughout memory, and to modify a linked list, we're just going to modify the references that are stored. So we're going to, like deleting a node, we just updated a reference to delete that node. When we're prepending, we create a new node and update some references to be able to get this list of size 3. Technically, what's inside the red box, that's still a linked list of size 3. It still exists. It's still there in memory. And if somebody has a reference to this node as their head of some list, they still have, effectively, a linked list of size 3, and they don't even care that we have this other node also referring to that linked list and calling it a linked list of size 4. We don't have to care. We effectively have 5 different linked lists in memory right now, but we only have to store memory for one linked list of size 4. We have an empty list of size 1, 2, 3, and 4. We are concerned right now about the linked list of size 4, but we do have all those linked lists in memory, but it's very efficient. We don't have 5 copies of a linked list. Like if we wanted to do the same thing with array list or arrays, we would have to have actually 5 different arrays in memory, and we'd be taking up quite a bit of memory. With a linked list, we can have all those in memory and just with pretty much optimal storage space. I mean, we have some extra references that that arrays don't have. But for certain use cases, they're very efficient. And when we remove an element, we're going to pop. All we really do is update top to refer to the second element instead of the first one. So we're going to say, okay, we still have that linked list of size 3 sitting there in memory. This linked list that's in the red box, it's still sitting there in memory. It didn't go anywhere. We just leveraged the fact that it exists by having next refer to it to prepend an extra element to the front of the linked list. But still sitting there. So when we pop -5, we're going to return the value, of course, and then update top to refer to top.next. And that's it. That's how we remove the first element of a linked list. We have a reference to the head of the linked list, and we just update that reference to be a reference to the second element instead of the first, the second node instead of the first node. And that's it. That's how we remove the first element from a linked list. And then that -5, that node, it's going to get garbage collected. We no longer have a reference to it. We have no way of accessing it. So Java's going to come along and say, give me that memory back. I want that memory back that I gave you for that node. So my point here is that these methods are very efficient. Very efficient operators. Push and pop are both what we call O of 1 operations. What this means is that no matter how large the stack is, these operations do the same amount of work. So whether we have our linked list of size 4 that we just saw, or a stack with 1 million elements, if we have a stack of 4 elements or a stack of 1 million elements, pushing is creating a node and setting its next to the old top of the stack, and removing is taking top and setting equal to a reference to the second node in the list. Nowhere in there do I care about the size of the stack when those methods are called. This is what we call O of 1 or constant time, meaning they do the same amount of work no matter how many elements are in the list. Compare this to our in the stack. Compare this to our linked list algorithm, size, toString, find, append. These all depended on the number of elements. And we had recursion to navigate through the list, where we recurse until we see null, which means we just went through the entire list, which is going to take quite a bit more time if that's a list of size 1 million versus a list of size 4. There was kind of one exception, find. Can shortcut if it actually does find the element it's looking for. What it's looking for might even be in the first node. It'll return sooner in that case. But if it doesn't find the element, it's going through the whole entire list. These are what we call O of 1 runtime methods, or linear, where in this case n would be the number of elements in the data structure. So O of n, meaning we got to navigate that whole thing. We got to look at every single element. With stack, and as we'll see with queue, we're restricted to just O of 1 operations. So push and pop, we're going to implement them both to be O of 1, and remove all the other functionality. So we're artificially restricting users of the stack to only use these efficient O of 1 operations, which is why toString, I wish I removed it from the slide, but I'll leave it there anyway. Even toString is not allowed with a stack because toString is O of n. It's got to navigate the whole list to print it out. Notice the implication of this. If you have a stack, you're using a straight-up stack with just push and pop, you can't ask that stack for its size. Size is an O of n operation. You can't do that. Now you could build your own custom stack where you track the size as things are pushed and popped. You just increment and decrement. You could do that and then just return that and get that O of 1. But the computer science concept of a stack doesn't have a size method. When you import a stack, you use a stack that somebody else has written. Usually it doesn't come with a size method. You can't ask it for its size. And this is why I don't like the data structures themselves in code, because I'll just use a linked list and do these operations on my linked list. And then if I do at some point need to know the size of my stack, I have that method sitting right there ready to call, and I can just be aware that it might take a while for that call to return. But if you use this data structure or any, like the built-in Java stack is going to be very similar. It's just going to have push and pop and maybe something else. We could look when we get to IntelliJ. But you can't ask the stack for its size. You want to do, hey, how many elements are in the stack? Can't do it. Just can't do it. Not allowed. So we're talking a little bit about runtime today. But runtime isn't really a focus in CSE 116. I think it'd be somewhat fair of a question on an interview, but I wouldn't expect any of your TAs to ask you about runtime. I just want to mention that because it's hard to talk about stack and queue without talking about it, because the question's going to come up like, why are we even using stack and queue? Why don't we just use linked lists and do everything with a linked list? And the answer is because of runtime. So I got to talk about linked lists I got to talk about runtime to be able to get that motivation of why are we even doing this. We're restricting ourselves to just O of 1 operations. The rest of runtime, a lot of runtime conversations in CSE 250. It's pretty much the entire course. It's runtime and also proofs. But the whole idea of choosing one data structure over another, the answer is almost always runtime. So choosing the right data structure for the right task is a question of runtime. Why choose a linked list over an array list? Runtime. One of them is going to be better, more efficient for your specific application. You want to choose the right one. But that's all 250. I don't want to steal all 250's thunder, and I don't have time to do all that. So we'll pretty much cap the conversation there. Later in the semester, we do bring up runtime, I think one more time, way late in the semester, like week 12, I want to say. We're going to talk about merge sort and talk about why that's O of n log n. But that's not for a long time. So just a kind of a side note on runtime analysis. There's lots of runtime analysis in your future, though, just not quite in 116. We're focused on showing you how programs run. Remember my breakdown, 115, just showing you how to get things done. And 116, how the computer actually works, how things actually run. And then 250, 331, and a lot of the rest of your career is how to do things efficiently. But we're not focused on that in 116. Why is stack.pop assigned to a variable? So pop returns the top value of the list and also removes that node from the underlying linked list. But it's just going to return a value t, and push just takes a value t. Whoever's using this stack doesn't care that we built it on a linked list. They just want to know that it has push and pop, and that those methods are presumed to be O of 1 operations. That's all people want. So we're going to return the value and remove it from the linked list. But that's why. Pop wasn't assigned a value, but X was assigned whatever pop returned. Okay. Any other questions before we get into Q? There should be questions. I know y'all got more questions than you ask, because I've been seeing the interview and quiz results, and they're poopy. I know you got questions. I want to know what they are. If there's a specific piece of data in the stack that you needed, is there a way to retrieve it? No. So this is part of what I'm saying is I would prefer to use a linked list and just use it as a stack and just be careful about my methods. Because then if I do have the need to get something that's halfway down the stack, if I'm just using a linked list, I'm just going to go halfway down the stack and grab it. And I would just be aware that that's going to be a slower operation. But if I use the stack class, either this one or what's built into any library out there from any language that you grab, no, you can't. You can't access an element that's not the top element of a stack. You just can't do it. To do that, what you would do is pop, 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 until you get to the element you're looking for, and then pop that one off as well. And then you could store all those in a data structure and then push, 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 push to get back to your stack. But that's what you would have to do. You'd have to just keep popping until you get to the element you want and completely destroy the stack that you had. Why can't we add more methods to pop? Oh, did I skip that one? Oops. Why can't we add more methods to pop? Like, you mean more methods to the stack? I mean, there's nothing physically stopping you from doing that, but the computer science concept of a stack is push and pop, and that's it. So just what we all agree on, you talk to somebody from halfway across the world who's also studied computer science or any software engineer out there in the industry, and you say stack, they're going to say, oh, you mean a data structure with push and pop. That's just what stack is. That's just the definition of a stack. So you could physically add more methods to this class. Nothing's stopping you from doing that. But it's technically not a stack anymore once you do that. Unless you add something like top or peak, which just returns the top element, the top value, without updating, without this line, without updating the linked list to remove that from the stack. It's generally accepted as a third method, but push and pop for sure required. Yeah, again, could you add a temp variable and cycle through it? Yeah, you could. Like, we could do that here. We could access any element we want because we have access to the linked list. It's just not a stack once we do that. Can you talk about the difference between the built-in stack class versus the one we write, and why we just use the built-in one? Why we wouldn't just use the built-in one? We would just use the built-in one. Like, you shouldn't, there's no need to use this. We're just using this as a lecture example to show you how a stack works. Same thing with the queue. I'm going to show you code just to show you how a queue works. Out there in the real world, or even on your homeworks, just use the built-in one. With the exception of linked lists, we're going to see linked lists and trees. Like, those are, so stacking queues. But those are things we're diving into in great detail. We want you to get your hands on those data structures and use them. You have to use our linked list and tree classes. For stack and queue, I wouldn't be mad if you just used the built-in ones. And outside of 116, unless another course is asking you to do the same thing, you're just going to use the built-in ones. These methods, these classes, stack and queue, that we're going to see, was written by Paul, and then I did a once-over last night on them. Like, well, there's not, but there could be bugs. There were bugs last night I actually found. But as opposed to what's built into whatever language you have, Java in our case, obviously, those classes have been worked on by teams of engineers for decades. They've been tested. They've withstood the test of time. Like, they're rock-solid implementations. You want to take advantage of that. You don't want to take advantage of something that your professor whipped up in 20 minutes or so. You want to take advantage of that functionality. But we want to show you how does a stack work, how does a queue work for the lecture examples. But yeah, outside of this class, out there in your career, if you're building your own stack class and then using that, stop. Don't do that. Just use the ones that are out there that already exist. All right, we ready for queues? All right, so a queue is our first in, first out. I forgot to say this with stack, but last in, first out was on the slide. First in, last out. I always say them backwards, but first in, first out, our FIFO data structure. We're all familiar with queues. You queue up in lines all the time. As to what they are, you can add elements to the end of the queue, and elements are removed from the front of the queue. So you queue up in the back, and whoever's been waiting forever at the front of this line, they're going to be the first ones to be removed from the queue. Just like a stack, we got two methods that define a queue: enqueue and dequeue. Enqueue, add an element to the end of the queue. Dequeue, remove an element from the front of the queue. Let's see this in action. We're going to create a new queue. We're going to enqueue three values, 1, 2, 3. And unlike the stack, we're going to get the reverse order. In this case, they're going to be in order, where 3 was the top of the stack. 1 is going to be the front of the queue. So 1 enqueued, 2 enqueued, 3 enqueued. And when we dequeue, we're going to dequeue from the front. X is going to store the value 1, and we remove that node containing the value 1 from the queue. And here's how we do it. A lot of code all at once. Let's go through it. So just like the stack, we're going to implement a queue using a linked list. As we're going to see, things are going to be just a little bit different. So we're going to store all the values in a linked list as an instance variable. But we have one issue that we come up with immediately with the queue. With a queue, we need to work from both ends of the linked list. With a stack, we only worked at the front of the linked list. We had a reference to the front, and that was fine. The reference to the first element in the linked list, we got everything done by doing that. With a queue, we need to work on both ends. Now, we could do the same thing, just store a reference to the first element in the linked list, but we would have a problem is that when we enqueue, we would have to append to the end of the list as opposed to prepend to the front of the list. And append, as we saw in the code last time, first requires you to navigate through the entire linked list and then actually append the value once you find a node with next of null. So you have to navigate the entire list first, which is slow. The whole point of stack and queue is we're restricting your functionality to only O of 1 operations, but append is O of n. So that's no good. We can't do it. We need to look elsewhere for other options, other solutions for this. And the answer is to store a reference to the first element in the linked list and store a reference to the last element in the linked list. So this adds a little bit more bookkeeping. It kind of looks like we have two lists here. We have one list, but we have two references to two different nodes. We have two references to nodes in the linked list. They might not be different nodes. But we have two references instead of just one. So a little bit more overhead, a little bit more bookkeeping. But other than that, our functionality is going to be similar. We just have extra lines to take care of this bookkeeping. So when we enqueue an element, we're just going to append. So this dot back, we're going to set next to a new node with the value that we have, the value that we're enqueuing, and then next of null. And then update this dot back to refer to that new node, because that's the new end of the linked list. So we're effectively doing the append part of the append method without all the recursion to get to the end of the list first. We're already at the end of the list because we're maintaining a reference to the end of the list. And we can just append and skip the navigating through the entire list, going dot next, dot next, dot next, bouncing all over memory. We can skip all that because we're storing an extra reference. So now we have O of 1 in queue, and we're feeling better about our efficiency of our implementation, which is if that's the whole point of a queue and a stack is for efficiency, we better make sure we're efficient. So that's the way we can get that done. And then we have a little extra bookkeeping. If this is the very first element that we're enqueuing, then we're going to create the linked list node and set back equal to that, which is very similar to pushing on a stack. But we also have to update front. So we want to make sure that we update both of these references, back and front. If we enqueue into an empty queue, back and front are going to refer to the same node. So we're going to get both of those references referring to the same node, the one node that we just created with the one single value in the queue. To dequeue, same thing as with a stack, except we have extra bookkeeping. So first, if the queue is empty, we're going to return null. And if the queue is not empty, we're going to go to the front of the queue, get the value so we can return it. And we're going to update front to refer to the second element in the linked list instead of the first element in the linked list. So far, everything's the same as a stack. The one difference is if we just dequeued the last element in the list, the last element in the queue, then we have to also update the back reference to be null. So we don't want the back reference to still be referring to the last node that was just removed, that was just dequeued. So we want to update back to also be null to indicate that this is an empty linked list now. And again, toString I wish wasn't there. So we added toString in the repo just so if you're running the examples, you can see what's in the stack and what's in the queue. You can print them to the screen and just see, for educational purposes. I should have removed them from the slides, but I'm leaving them. Even when I go back and update, I'll leave them. Maybe next semester I'll get rid of them. It might bug me. So let's see this in action. Again, this abbreviated memory diagram. I wish I had time to do a full memory diagram. They just take so long. They take a long time. Hopefully I'll get another one in maybe next week. We can get a good linked list memory diagram. But we did get one on Monday, so I'm happy with that. So we're going to start a new queue. Front and back are both going to refer to null, which is the lack of a reference. We're going to, in Q3, when we do that, we're creating a new node, and we're making sure we're updating front and back to both refer to that node. We want to make sure they both refer to this node that we created. There's only one node, so it is both the front and back of the list, or the queue. In Q7, when we enqueue, next equals a new node with the value that we're enqueuing and next of null, and then update back to be a reference to the new node. When we enqueue 2, take back, next equals the new node, and then update back to be the next one. So notice that when we enqueued on an empty list, an empty queue, a queue of size 1 or a queue of size 2, it takes me the same amount of time to explain it. Like it's the same amount of work. This is what we want. This is our O of 1 work. We're doing the same steps, same amount of work. Nothing depends on the size of the queue. This can be a queue of size 1,000,000. Enqueue is go to that reference of back, set its next equal to a new node, and then update back to refer to that node. That's what it's going to do every single time, regardless of how many people are queued up waiting to get to the front of this line. When we dequeue from the front. And we do even less work here. We just update front to be a reference to the next node. And we have a little bit of bookkeeping, making sure we store 3 and then update the reference and then return 3. So X gets the value 3, and that node gets garbage collected. It's gone. It's not in memory anymore. How do we know that front and back are references to the front and back of the queue and not just two arbitrary variable names? I'm not quite sure how to answer this one. I mean, they are arbitrary variable names, but we chose names that made sense for the context. I think front and back make more sense. They don't have to be references to the front and back of the list, but the way we wrote the queue class, we made sure that they're always going to be references to the front and back of the list. So we made sure that the variable names made sense the way we wrote the code. But you could, I mean, I've seen the assignments out there. Some of y'all choose some really crappy variable names. You can name them whatever you want and use them however you want. But we name them front and back because that makes the most sense. Please use better variable names, by the way. The reason, I mean, either you're gonna or you're not. But if you choose better variable names, it's just easier to help you in office hours. If you come to office hours and your variable names are A, B, C, D, E, F, it's just very hard to read that code. And it takes longer to help you in office hours. Sometimes we might just give up and say, I can't even read your code. It's giving me a headache. I'm going to the next student in the queue. Hopefully we don't. Hopefully the TAs don't do that. But you can get worse answers if you have worse variable names. So just a heads up. I mean, you're going to do what you're going to do. But so we dequeue again. Again, same amount of work, constant work. We return the value and then update front to be a reference to the next node in the list. And you can see why I stopped crossing out my nodes. I'll probably start graying these ones out too in the abbreviated memory diagrams because I crossed it right through the numbers here. And then when we dequeue again, we got to make sure that we're updating back as well. So instead of just having front refer to the next element in the list, we also have to update back to be null when we dequeue the very last element in the list. And our entire list gets garbage collected. We don't have references to those nodes anymore. The whole thing's gone. Then we dequeue from an empty queue. In most implementations, this will just give you an error. In ours, we have some error-tolerant code, so we're going to return null instead of just crashing. But we still do crash. So null, what null is the lack of a reference. Null means this variable is supposed to refer to an object on the heap, and it doesn't. It doesn't, so we store null there instead to show that this doesn't refer to anything at the moment. Int isn't supposed to store a reference. It stores a value that represents an integer. It's not supposed to store a reference at all. So it doesn't make sense for any of our primitive values that don't store references to store null, because how can something that's not even supposed to store a reference to nothing? Doesn't make sense. Java agrees, program crashes. We can't store null in int, so once x equals null, program crashes because what's x supposed to store? It could get set to 0. It was suggested in the other lecture, but it's just not what Java does. Crashes. Can't do it. So our program does crash when we dequeue from an empty queue if we're storing the dequeued value in a primitive variable. All right, I want to show, I got a lot less time than I did in the other lecture, but I still want to do this. So let's hop over to IntelliJ. I want to show something. We have an entire lecture on this next Friday, but I want to at least give you a taste of it now, because you're starting to get to the point in your programming test where this can be very useful. So I'm going to set what's called a breakpoint. So in my code, I'm just going to the first line in main. I'm going to go over here and click, and that's going to set a breakpoint. And when I run this code, I'm going to click this bug button, either here, wherever you see a play button, right next to it's the debug button, and I'm going to run the debugger. What this does is run through my code until it sees a breakpoint. Once it reaches a line of code with a breakpoint, it's going to stop everything and show you the state of memory. It's going to show you all of the same information that you're putting on your memory diagrams in this interface down here. So we set that on the first line. There's nothing interesting to see right now. It's just args and nothing. But if we click through, I'll just click through a little bit here. You can click this button to advance your code one line at a time. And we can see all the frames on the stack right here. Right here I have the main stack frame, which has a queue with just the value 1 in it, because we've only enqueued 1. We have a stack frame for enqueue with this equaling a reference to a queue at 446, just the random number Java gave us for this execution.